Okay, so we left off on Rutherford's alpha particle scattering experiment. It's probably one of the most famous experiments of that time. It and the photoelectric effect would be the two big guys. What Rutherford did was he took these alpha particles, which were emitted from radioactive substances, and remember yesterday or the last video, we said that an alpha particle was simply the nucleus of a helium atom. So it has 2 protons and 2 neutrons inside of it, but they're together as one unit. They're not separate entities, so they're bound together as one unit. And so when the radioactive substance emitted it, it would be emitting the 2 protons and the 2 neutrons together. So Rutherford was able to collect these, and he shot them at this really thin sheet of gold foil. Okay, so here are the alpha particles, and he's shooting them in at this really thin sheet of gold foil. Now he wanted it really thin because I almost did all the reallys again. Because he imagined that if he got it thin enough, it would be 1 atom thick. And so as this alpha particle, which would have a positive 2 charge, comes in, it's interfering with just the 1 atom. Okay, so now in behind this really thin sheet of gold foil, he put a detector so that it would pick up anything that happened. Like, so if these alpha particles came off and the angle with which they came off, so he has this very sensitive detector in behind that is going to detect what's going on. And it would be something that would be sensitive to light, some kind of a photosensitive detector probably. Okay, now so he imagined that if Thomson was right, if these atoms were really like the raisin bun or plum pudding model, if Thomson was right, he thought that the atom, the beam should pass through with only slight bends because of the attraction and repulsion forces, right? So the positives would repel, but the negatives would attract, and so they'd kind of cancel each other out, and there should be slight bends, okay? What he found was that most of the beam went straight through as if it was passing through empty space, and that only 1 in 5,000 alpha particles ended up being deflected. And now those 1 in 5,000 were deflected almost straight back, as if they had encountered some huge, massive positive charge that caused this little positive dude to come running back out. Okay? So almost all of the particles went straight through as if empty space, but 1 in 5,000 came straight back, okay? As if they had encountered a huge, massive, he thought it had to be bigger. The positive 2, the alpha particle is fairly large compared to an electron, so whatever was in there had to be bigger than that, and it had to be positive to repel it, okay? His conclusion then was that most of the atom must have been made up of empty space, and that's why the beam passed straight through. He concluded that inside the atom there must be a massive positive charge, and he called this the nucleus. And he assumed it was in the middle of the atom. And he assumed that the electrons then must be orbiting around this massive positive charge. Okay? And that's why, like, there was very little attraction or repulsion. That's why most of the beams passed straight through. But 1 in 5,000. So he did some calculations on this 1 in 5,000 that came back. And what he figured was, if the atom was the size of the room that you're in, then the nucleus would be about the size of the tip of this pen. Okay? And that's why then a beam of alpha particles would pass straight through without very often any one of them coming close to the tip of this pin if they had the whole room to pass through. Okay? And that's why only 1 in 5,000 came back. Okay? Now, in real life, in case you were wondering, the atom is not the size of the room that you're in. It's significantly smaller, which means the nucleus is significantly tinier than the tip of this pen. And that will come into play when we get into the nuclear unit. But this whole idea that the massive positive charge with the electrons orbiting around it is why this model became known as the solar system model. Okay, the nuclear model because he called the center mass the nucleus, but the solar system model because it's looking like the sun with the planets orbiting around, the nucleus with the electrons orbiting around. Okay, now unfortunately his model had a few limitations. Okay, after he proposed it and people were like, oh, this is good, then they were like, oh, but wait, there's a few things that don't seem to get explained here. So they're known as his limitations. Okay? One is that we know from the electromagnetism unit that an electron that is being accelerated, charged particle that's accelerated, gives off energy. Right? It gives off EM rays. Okay? And so if there's an electron orbiting the nucleus, it's accelerating, right? Because that's centripetal motion. It has a centripetal acceleration, which means it's giving off energy. So it's in this balanced spot at the moment where like gravity is pulling it down, acting as that centripetal force. And remember, centripetal force is mv squared over r. But as it gives off energy, which would be kinetic energy, it's going to lose speed. And as it loses speed, it's going to slow down, and as it slows down, gravity's going to win, and it's going to begin to pull it in. And so if the electrons really are orbiting the way Rutherford suggests, they're going to lose energy as they orbit, and they're going to spiral into the nucleus, and the whole time giving off energy. Okay? Calculation-wise, when they checked to see how long an electron could stay in an orbit like that, they found that this atom would only be stable for 1/100,000,000th of a second. This might be a flaw. If every atom collapsed after 1/100,000,000th of a second, we wouldn't have any atoms left by now. Okay, so... and not only would it collapse then, it would give off this continuous spectrum of light while the electron was spiraling in. So you would see this continuous spectrum of light. You would see these like rainbows all over the place as it was collapsing. So clearly fatal flaws in his model, just because there's no way that this could be the true model of the atom. Okay? So that's Rutherford's model of the atom. The person that comes up next to try to fix this is Niels Bohr. And now, most of you in chemistry would refer to the Bohr-Rutherford model, but really in the beginning, it's called the Bohr-Rutherford model because Bohr built his model on Rutherford. Okay, so, and he called it the Bohr model. Looking back, we would refer to it as the Bohr-Rutherford model. And this is 1913. So only 2 years after Rutherford, Bohr puts out a model that he builds on Rutherford's. He says, okay, Rutherford's was unstable. It has these limitations. The limitation that electrons are accelerating, so they're giving off energy, and that giving off energy means they're losing speed, and the losing speed means gravity's going to pull them in. They're going to give off a continuous spectrum of light, and the whole atom will be unstable. It will only last for 1/100,000,000th of a second. So we need to change a few things. And so that's the next video. What does Bohr do to make Rutherford's